is actually something which deals with the central force. So this is something which we are going to do now. Okay. So what happens is whenever we are talking about something which is related to Newton's law, okay, or Coulomb's law, we are more or less concerned about the distance. So if we have two masses and we want to know what is the force between them, we do consider the distance between them as an important factor. And such study or such study of force is mainly comes under the purview of central force. Okay, so central force is very much closely related to nature, and hence we are going to study this. We are also going to do some assumptions. Let's say, for example, you have got a very heavy ball. Okay, you have got a very heavy ball. Let's say a ball made up of cement or something, and then you have got a plastic ball. Now if you are hitting that ball, which is actually very heavy, okay, and you want to hit it with a plastic ball, probably the plastic ball will get scattered without having much impact on the heavier ball. Okay, so these kind of ideas are also important to understand central force problem, so that we can reduce the complicated problems into simpler ones, but then don't deviate far from reality. Okay, so whenever we have something like, let's say, the motion of the planet, so motion of the planet with respect to the sun, that also comes under the central force. So if we are studying Kepler's law, okay, which is actually governs the motion of the planet, it actually comes under the study of central force. So in this chapter, we are also going to derive Kepler's law. Okay. So apart from that, if we talk about planet, we talk about satellites. Okay, or we can talk about the moon, the natural satellite. Okay, everywhere we do have the application of Newton's law. So here is Newton's inverse square law of gravitation, and of course the Kepler's law, as I said. Okay, so inverse square law of gravitation you have, so that means you have got two masses, m1 m2 divided by r square multiplied by the gravitational constant. Okay, so that's what is central force is all about. Okay, and then we have got a number of examples, and as I said, this is very much closely related to nature. So even if we consider something like Coulomb's law and we are talking about charges, that again comes under the central force. Okay, so let's take some more example. Let's say the van der Waals force. So you know, van der Waals force is actually a very weak force. Okay, if you're considering some atoms or gas molecules, there is some kind of force which is acting, but then because the masses contribution of the masses is minimum in such system, the force that acts is very weak, and of course depends on the distance, but then this also comes under the central force. So such examples are also there. Okay, and then you have got the Hooke's law of elasticity. So if you remember Hooke's law of elasticity, okay, and if you consider something like a simple harmonic motion, we do consider this as a part of central force. So if we say, let's say F is proportional to X, so this X is nothing but the displacement from the mean position. Okay, and then if you remember that this displacement is opposite to the direction of force, okay, so it does have that effect. So we can always take it to be minus kx. Okay, so if we take these examples, these all examples comes under central force. So you see the form is not fixed. If you consider this inverse square law, this is 1 by r square. Okay, and so this is there, depends on the distance, but then this is directly proportional to the displacement x. So this is also central force, but it is not mandatory that it should be inversely proportional to r square or directly proportional to r or x. Not really. Okay, it only depends on the distance. So this basically says that f should be a function of distance. That is more important. Okay, so this is where we talk about this as the central force, and then we consider it along the line m is equal to 0. Okay, and what happens is whenever you are considering the force, let's say we have got two bodies of mass, let's say m1 and m2, this will always the force will always act along these line joining the two. These two are of course imaginary lines. Okay, this line is an imaginary line, and the force will act along this line. Okay, so this is what is meant by this, and then this is nothing but a function of r. Okay, so if we just you've seen so many examples, so can we just define the central force? Yeah. So if I just go for a simple definition, I can say what is a central force. Okay, so a central force is basically one which is always directed away from, okay, it is away from or towards a fixed center. So see, if you are considering something like a centripetal force or a centrifugal force, it is directed either towards or away, okay, and that comes under something which we call as the central force, okay, and the magnitude of which is a function only of the distance from that fixed center, okay. So if you consider what is the magnitude of that central force, this will only be actually depending on the distance from that fixed center, okay. So these factors are important to consider, but then it should be acting towards a fixed center. That is what is the underlying idea here. So we do have an origin, okay, that is always there whenever you are considering a central force. So these things we are going to see in the near future of the classes, okay. So it's a conservative force. That's very important by nature. A conservative force, so that's very important, okay. So we do consider that the total energy will more or less be constant, okay. In some cases it might be even zero, okay. And then of course the angular momentum is constant. This is very important. The angular momentum is constant. Now what happens if the angular momentum is not constant, okay, and the energy is not constant? See, we talked about holonomic and non-holonomic constant at the beginning, and then if we talk about something which keeps on varying, identifying a perfect equation for that becomes very difficult. So I did ask you this question in your quiz also, that if you're considering a body moving without slipping, okay, on a rough surface, will it be holonomic or non-holonomic? Well, most of you have written as non-holonomic. That's correct, right? For the simple reason that if it is on a rough surface, you can't really define a mathematical equation for this because it's rough, right? It doesn't need pattern, okay? That's very important. So similarly, if you're considering a central force, the conservation of angular momentum plays a very important role, okay? And then we are talking about the motion being planar. So in planar, I mean that the motion is along the XY axis. So now we are considering only a two-dimensional system, and we are considering it to be on an XY axis. So motion is planar, okay? So as per convention and physically, we know that if this force is less than zero, we basically call it as an attractive force, okay? This is important again because this is the convention that is always being followed. And if Fr is greater than zero, that means the force that is acting is positive. We are more or less talking about a repulsive force. Okay. So we already know about this attractive force and repulsive force. If you remember the relation between force and potential, which you might have come across a number of times, we do say that F is equal to minus dV by dr. Okay. So this relation is very popular. I think this is something which you might have come across, but we are going to see this later also. Okay, you might be coming across this in quantum mechanics also. So we have got a minus sign. So this minus sign actually signifies that this is nothing but we are talking about an attractive force here. Okay, so if you actually draw a potential diagram, there is also a potential diagram that can be drawn between the force and the distance. Okay, between the force and the distance, and eventually you will see that the potential diagram will be something like this. Okay, so I'm not going to explain this, but I think this is something which you're going to come across in your future classes. So see, this is the negative part. So this is the negative part. That means in the graph, this is the attractive part that we are talking about. This is the repulsive part that we are talking about. Okay, so you're going to get these examples more and more in the future classes of many topics. Okay, many topics in physics, be it nuclear physics, or we're talking even about classical physics, even in quantum mechanics and so on. So all these does have this importance. Okay, that's very important. Okay, so let's consider one problem. Okay, let's consider one problem based on gravitation, because this is something which we already have a very good idea about. Okay, we do have two bodies. Okay, and the gravitational law acts on that. So that's Newton's law of gravitation. Okay, so let's consider this. So what we do is we consider a two-body problem. You know that if we are considering something very practical, it might not be a two-body problem. It might be a 10-body problem, 15-body problem. And even if you're considering that kind of system, we have to first consider what is the force of attraction, let's say, between the first particle and the second particle, first particle and the third particle, first particle and the fourth particle, okay? Also second particle and the third particle, all of them, okay? And all of them has to be considered. So when you go into a real practical problem, definitely you need to have more and more parameters involved, okay? But now what we're doing is we are considering just a two body system, okay? Two body system. And then we are trying to see if we can reduce it to a one body problem. Now it can be reduced to a one body problem, okay, if there are certain conditions that is being observed, okay? So let's say for example, if one of the mass is heavy compared to the second, okay, then we can actually reduce it to a one body problem. This is what we are going to see now, okay. So we can reduce this two body problem to a one body problem, okay. So what happens is the heavy body actually can be considered to be the origin. Now, why the heavy body can be considered as the origin? As I said that initially, if you are having a very heavy ball and if you are hitting it with a plastic ball, you see that the heavy body doesn't move around. Okay, it's basically there. The plastic ball gets deflected or scattered or reflected or whatever. Okay, so that means the heavy ball can be considered as the origin of the system. Okay, so this is something which you are going to consider here. So since we said that central force, we are considering a planar motion. So we are just going to consider the two coordinates. What are those two coordinates? The x coordinate and the y coordinate. Okay. So we can either consider it to be the x coordinate and the y coordinate, or the r and the theta coordinate. Okay. Depending on what kind of coordinate system we are dealing with. So if we are dealing with a polar coordinate system, okay, I'm not talking about generalized coordinates here. Okay, we are talking about representation of a particular point. Okay, in terms of x and y coordinate, the Cartesian coordinate, or r and theta, the polar coordinate. So let me just give you some brief before we actually consider reducing a two body problem into a one body problem. Okay, so this is basically a plane polar coordinate, which we already know, and we are going to see how we are going to tackle it in terms of the other coordinate system. Okay, so let's say this is, I think, very simple. We do have a x-axis and the y-axis. Okay, and we do have, let's say, a position vector. Okay, this r bar will actually represent a position vector in any time t. So that time t is very important. And if you consider this r, it has got a coordinate of x and y. Okay, so this is basically in terms of Cartesian coordinate that we're talking about. Okay, and let's say after a time dt, okay, this is t plus dt, the particle reaches this particular point. Okay, it's not that it is following a constant radius. If it is a constant radius, it will follow a circular path. I'm not saying that. Okay, what we are saying is that after a time dt, the particle reaches this particular point. Okay, so that means this length would be nothing but r plus dr. Okay, after a time t plus dt. What will be the coordinate now? X plus delta x, y plus delta y. So delta x and delta y is a very, very small change. This is what is done in Cartesian coordinates. See, this is not important. Even if I don't teach you, you know it. But then I just thought, okay, let me just do it, because this is something which you'll need in the near future. Okay. So if we just now write it down in terms of theta and r, how can we write it down? Okay. So in terms of theta and r, what we can do is, we have got the x coordinate and the y coordinate again. But then now we are not going to write it down in terms of the x-axis or the y-axis. Okay. No, we are not going to do that. We are going to write it down in terms of r and theta, right? So if we do that, okay, what we do is this. We have the position vector, which is nothing but r bar, which is nothing but the distance from the origin, and it is actually inclined at an angle theta with the x-axis. That's very important. Okay, it is inclined at an angle theta with the x-axis. So if you want to actually define this position, we can simply say that the position is r, which is the distance from the origin to that particular point. Okay, making an angle theta with respect to the x-axis. Okay, so in general we say that r is nothing but the radial distance from the origin. So this is a bit technical, but then we know it because we are science people, right? But then this is very logical also. It's very simple. And what is theta? Theta is nothing but the angle. Okay, and this should be le, or let's say ld. Okay, angle between p bar and the positive x-axis. So maybe I can just write down this entire line as p bar. Okay, or I can simply write it down as r bar also, doesn't matter. And the entire x-axis, we have the angle as theta. So this was the position, okay, at this particular point. And then let's say after a time t, it goes to this particular point. So then the position vector will change to r bar plus dr bar. That means the radial distance will change to that, and the angle will change to theta plus d theta. So that means this small angle is nothing but d theta. This is d theta. Or in other words, we can say that if this entire angle can be taken as theta plus d theta, right? So that is the angle. Now, what is the direction? Okay, what is the direction? That is very important, because we are talking about vectors here. radial distance, angle. So we are more or less concerned about vectors, right? So in general, we say that x will basically now be x and y will be now be represented as r and theta. Okay, but then what about the direction? So whenever we are considering a normal vector symbol, okay, normal vector system, we represent the x-axis with I cap, okay, which does not change, and represent the y-axis with j cap, which does not change. So it will remain more or less fixed. So if you take a differentiation of, understand this, okay, if we take a differentiation of I cap or j cap, this will always remain 0. But this is not true in this particular case. Okay, this is not true in this particular case. Why? Because at this particular point, okay, the direction is r cap radially outward. This is the radial direction, r cap. Okay, the direction of r bar is radially outward. But at this particular point, it does not remain along this direction. Okay, sorry, this is not right. I should make it parallel to this. Okay, this line. Okay, so this remains this. So this is not happening. This is not happening because it is following a curved path. So that means the direction will be radially outward. So the direction changes to this. Okay, r cap plus dr cap. So that is the reason that we cannot say that we can represent it by I cap or r cap. Not possible. Okay, we are representing it by r cap and theta cap because the direction is going to change. Okay, bit more on that. That means that if I take the differentiation with respect to time for r cap, it cannot be 0 because this r cap will keep on changing and this d theta cap will also keep on changing. Okay, see, this was theta, it became d theta, and then it will become something else. So this theta will keep on changing here. Okay, so this theta will keep on changing. But when we talk about I and j, I is along x-axis and j is along y-axis. That's all. Okay, it's not changing its direction. Okay, but here it is changing its direction. So in simple words, we cannot say that dr cap by dt is equal to 0. It won't be 0. Okay, the simple reason is the underlying factor r cap and theta cap changes direction. That's very important. So what do we get from here? That we do have some important parameters. Okay, and those parameters are nothing but r. Okay, what the parameters are r, theta, which can be written as r dot. Okay, because you know that whenever we are talking about angular displacement, okay, r will change with time. Okay, that means the angle theta will change. Okay, so theta is nothing but r dot. Okay, and then acceleration is r double dot. You can take it in different forms. Okay, so this is just understanding. This probably might not be asked in your exam also. This should not be even taught also in classical mechanics because this is something which you might have learned earlier. Okay, but then I thought this is important because all of us do become a bit rusty if we don't study these topics. Okay, so this, if this idea is clear, the underlying factor here is that whenever we are considering the polar coordinate, this may be 0 in Cartesian, but in polar this will not be 0. Okay, so that is very important. So this idea we are going to use. So what we're going to consider now is we are going to consider a two-body problem, and we are going to consider the idea of reduced mass. So what do I mean by a two-body problem? Let's say I have got a mass m1 on here and we have got a mass m2 here. So you've got two masses m1 and m2. Okay, and if you consider this two-body system, this is a two-body system because there are two masses here. It can be reduced to effectively the topic might get repeated. So don't worry. Let's just an m2 as the two particles. Okay, right now. And then let's say this is your origin. This is your origin. Okay, distance of mass m1 is r1 and distance of mass m2 is r2. Okay, and then if we take vectors, what we can do is this: the distance between m1 and m2 is r. This is actually r bar. This is r bar. Very important. So if this is r bar, by vectors what we understand is r2, okay, plus r bar. You're going here, or you're going from here to here directly. which is R1. So that means R2 plus R bar, okay, is equal to R1, or R bar is equal to R1 minus R2. So this is a simple idea of vectors. I think this is not complicated. You can already understand this, right? Okay, let's rub this off. Looks too confusing. Okay, so we have this. Okay, so this is important here. Okay, and when we use this, we actually get this idea. So that means that R1 bar, R1 and R2 are nothing but the position vectors with respect to the origin. Okay, in an inertial frame of reference. So you will come across these terms of inertial frame again and again. So we do study an inertial frame because it's basically a simple idea where the system is moving at a constant velocity. So that means this m1 and m2 both are moving at the same constant velocity. Okay, so if we are considering this entire system together, we are considering it in one inertial frame of reference. Okay, so we are considering that frame. So I think frame is already clear to all of us, because we are going to study relativity there. We are going to study more about frames. I will take that. That is also in the classical mechanics. But then I think it's known to us that whenever you are standing and a train is moving, someone on the train is on a different frame of reference compared to you being on ground, right? So these are some ideas of frames of reference. So if you are traveling to the moon on a spaceship, the speed with which you travel and reach the moon, okay, will be in a different frame of reference compared to someone who is watching you from the earth. That will be again a different frame of reference, right? So this is something which you are going to see in the future. But right now, I'm just going to consider this inertial frame of reference. So again, R1 bar minus R2 bar is equal to R, and this is nothing but the vector distance of M1 from M2. So let's represent everything in terms of vectors. I think that is very important. Okay, and then what happens is these particles are exerting gravitational force on each other, right? I think this is not very complicated. They do exert a gravitational force, okay, because these are having masses, okay, and thank God they don't have charge. Otherwise, we also have to consider the Coulomb force, right? So right now we're not considering that. So they're exerting gravitational force on each other, hence central force. Okay. So if they are having charge, then we will consider only the Coulomb force. Now you might ask me, even if they are charged, why we are not considering the gravitational force? So when you have a clear idea of the type of forces that we have in nature, we do have this electrostatic force, we do have gravitational force, we do have nuclear force, okay, and we have a weak force. So nuclear force is very strong. When we are talking about gravitational force, it's weak. And when we are talking about Coulomb force, it is much stronger compared to the gravitational force. So if it is much stronger compared to the gravitational force, we just consider the Coulomb force. It doesn't really mean that the gravitational force is not there. It's there, but it's negligible. Okay. So here we are considering a gravitational force because we are considering these two masses as chargeless. Okay. They do not have any charge. So let's consider F12 bar. So that means the force that one is exerting on the second particle, or F21 bar is nothing but the force that the second particle is exerting on the first particle. Okay, so force experienced by M1 due to M2 and M2 due to M1. Simple representation. But then here we should also know that F12 and F21 are equal and opposite, because we do have the Newton's second or third law, right? To every action there is an equal and opposite reaction. So F12 would be minus of F21, common sense, right? So this idea also we are going to use. So if we just write down the equation of motion, we have got mass into acceleration is equal to force. But now we are going to write down everything in terms of vector. So the mass, let's consider the force that is acting on the first particle, M1. Okay, so it will be mass into acceleration. Acceleration will be nothing but the second differential order of the rate of change of position, right? So basically d2 r1 bar dt square is the acceleration, okay, where r1 is the position vector of the first particle, and f12 is nothing but the force exerted by the first particle on the second particle. That is important. Okay, so this is there. Again, we can consider for the second particle. So we have got f21 bar. Now you see, we are going to use reduced mass. That means in some way or the other, we should combine these two equations, and that is what we are going to do. Okay, so we have got these two equations, very simple idea. And by Newton's third law, we know that F12 bar is equal to minus F21 bar, which is nothing but F6. Okay, so we're just considering it to be F. So one would be F, other one would be minus F. because they are obviously the equal, okay? They're equal and opposite. So F12 is equal to minus F21. So can we just modify it a bit? We are just going to replace this F12 by just minus F, and we are going to replace F21 by F. So we can just replace it here, we can just replace it here, and then we have got these two equations, okay? Can we combine them? Yes. What we can do is we can subtract one from the other and then try to combine them. So if we just subtract it, this minus this, it will give you R1 minus R2. I think you already have a hint that this will be nothing but R bar, and this would be nothing but, you can take the minus out, it will be 1 by M1 plus 1 by M2 into F. You should do your calculations on your own, okay? That is very important. And then you see this term, this particular term will be actually considered as 1, which is the reduced mass. How do we do it? It's very simple. I'm going a bit fast because I know you already understand this, okay? This is very simple. D2 R bar dt square in place of R1 minus R2, and then this is left as it is. And then since we're defining a direction, so let's put R cap now. Let's write down the direction also, which will keep on changing, okay, at particular point. So F is the magnitude of the force, okay? And this I don't know what I've written, probably have some errors here, okay? And R cap is the unit vector along R bar, okay? So basically R cap is the position, okay, function of R, okay, magnitude of force, and which is a function of R, sorry, okay, so this is a function of R, and then R cap is the unit vector R bar. Now what we will do with 1 by M1 plus 1 by M2, we'll just put it as 1 by mu. This is how we represent the reduced mass. Mu is the reduced mass, okay? So can we zoom in a bit? Zooms too much sometimes. Okay, yeah, this is okay. So we have got 1 by mu is equal to 1 by M1 plus 1 by M2. And then we can just take it, and then mu is equal to M1 M2 divided by M1 plus M2. This quantity is called the reduced mass of the two particles. So you see, I have combined both the particle into an entire system. That means this is the equation of motion for the two particle system or the two body system, okay? So this is reduced mass with dimension is mass. Why? Because this is kg into kg, kg square. This is kg plus kg, so unit will remain as kg. So kg square, kg gets cancelled, this will remain as kg, okay? If I take it in kg, of course it might be in gram and all. So the dimension is okay, right? So it's reduced mass. So this is kg, this is acceleration, it is of course equal to force, okay? So that is what we are considering. And then there is a negative sign. What does it show? That this is nothing but attractive force. Two masses are being attractive in nature, okay? This represents a one body problem. So what I want to do is probably in the next class, I'm going to give you an example of how we can actually consider a one body problem to do better understand, to have a better understanding of, let's say, a nucleon system. Okay, you have a heavier mass, okay, which is being scattered by a lighter nuclei. Which mass should we consider? Do we need to really consider mu, or we can just consider the mass of the heavy particle, and how?